So we're talking about reversible and irreversible processes. I'm going to kind of go over this whole thing again, since we have time, really, because both Alice and I have looked at the homework, and there's really not a whole lot there. So, but we'll hit it again. It'll be good practice. Reversible, irreversible. What was the difference? One can go back and forth. Which one can go back and forth? Reversible. Now, what does back and forth mean?
From final to initial.
Ooh, from final to initial, yes. Right? And on an engineering perspective way, I mean, if you're physically going to do this, you know intermediate phases? How about on a... Since we're talking about thermodynamics, time really doesn't fit in. You're not even supposed to mention time. But practically speaking, which one has to... It could happen infinitesimally slowly and be at equilibrium every single point of the way. Reversible, right? Irreversible is something that's just supposed to happen like that, right? You can't go back. Exactly, right? Now, mathematically speaking, how do you represent the difference between a reversible process and a irreversible process? There are going to be two little symbols. Anybody know? I'm thinking of change.
Oh, would that be the big delta and the little delta?
Okay, big delta is the change for reversible or irreversible? Irreversible, right? You can't go back. It's done. You can't go back to the original state. Now, when they're talking about original state, they're talking about, the energy, all the conditions. So there is no little delta, though, for irreversible. What are they going to use? Okay, now I'll give you a hint. You measured, I'll use the technical jargon, see if you're following me. You calculated instantaneous slope in calculus. What did you use to represent? I'm calculating instantaneous slope, instantaneous rate of change. Little d. Okay, you use little d. And that was when there's how many things that could possibly change? How many variables could possibly change at any one time? Just one, right? Use little d. Okay. So, before we jump back a little bit, let's just finish this reversible and irreversible talk. Something happened, huh? Okay. So we want to jump. Pay attention now. We want to jump. This could very well be a really good exam question. We want to jump from there down to there. They both work, right? And I had a syringe, but you can kind of just see if this was the top of the syringe, and the syringe is my system. And it's definitely not isolated because it can push up on the environment, right? And create random motion or orderly motion in the environment. Orderly, right? It's called the W word, work. Okay, so my little syringe system, if it's pushing up on its surroundings, is my system gaining energy or losing energy? It did work on the surroundings. It's losing energy. So that little W, whatever we get, should be positive or negative. Negative, right? Because look at these little infinitesimal changes. You could write, we had it before, whether you have little infinitesimal changes or a big macroscopic change, right? If your system does work, that W is going to be negative, or the dW is going to be negative, right? It's an infinitesimal amount of work. Okay. The Q, how could that syringe system, what was the Q? Heat. Heat. So if this little syringe dude loses heat to the surroundings, my little Q would be positive or negative. It's losing heat to the surroundings. It'd be negative because you're losing energy again, right? Because you want to recognize that du, that, what was U called? What was U called? Internal energy. And for a perfect gas, there's not really a whole lot to add up there. All these little dots can do is fly around. They can't rotate, they can't vibrate, they can't do anything. But the point is if you find out all the different energies, all the different energy modes, add up all that energy, that's total internal energy. Okay, so the point is, the system does work, little w's negative, but you're going to end up having a different equation, whether it's reversible or irreversible work. That equation, W equals minus P external delta V. Have my little syringe, pushes up on the surroundings, right? I can measure that delta V. Just read the little syringe markings, right? Final mass initial. What's PX? Yeah. So it would be atmospheric pressure, whatever it is. And it has to be what? That external pressure. Can it change? Has to be constant. Otherwise, you can't use that equation, right? Because if the pressure changes, it's going to take more work when that pressure is pushing down harder. Okay. So that's that equation. W is minus Px delta V. So the little Ex probably stands for external. Yeah, and it can't change on you. So let's do that exact same idea with the piston, except it's kind of like what Alice and folks were saying. You're at equilibrium every moment along the way. So you're going to do some work because you're going to end up pushing the surroundings and doing work on it, creating orderly motion, but you're going infinitesimally slowly so that you can go back and forth. You're at equilibrium every point of the way. According to this little plot, and it might be kind of hard to see. It is hard to see. Do you do more work with reversible or irreversible? What's that? You do more work when it's reversible. It's hard to see in that plot, isn't it? I think it is. Because work... Now first, if you multiply pressure units times volume units in our metric system, what unit would you get? You get joules, big J. We did that in the concept review. And we better because work is energy. Okay. So change in volume times the pressure. Here's our change in volume. Here's our pressure. You multiply the two, right? Get area, P delta V. So the area under the curve here is really just the amount of work that you're going to do, right? And notice P external is constant. That's why it's a constant top. The reversible equation, natural log function. So it's very similar. You just plot it out. What's the pressure, right? So you just plot it out, and you end up getting this plot for reversible, how the pressure is changing with volume. Right? It's inversely proportional. So you get more area, more work, if you do it reversibly. Is what they're trying to get at there. It's not very clear, but reversible, you always get more work. So my question to you is, how do you go from here to here? Okay. Oh, all of this is assuming ideal gas. All this is assuming ideal gas. Because look at that. They have P equals nRT over V. The equation of state is an ideal gas. Yeah, they're assuming ideal gas. Otherwise, our life would be much more ugly. Especially doing this derivation. Okay, we're going to start with this. We want it... I mean, the idea is the same. you're changing volume, multiply it by because force times distance, and you get the work. So the idea is the same, except now we have to do it in infinitesimally small steps. So mathematically, we better replace that big macroscopic delta with what symbol? Little d. You better replace that with a little d. Okay, so we have minus p external. Now, if we move that syringe just up an infinitesimal amount, dv length, we're just going to do an infinitesimal amount of work. So you put a dw over there. Okay. And how do you add up all these infinitesimal little steps? What symbol are you supposed to use? Sigma is really for adding 6 plus 12 plus 8 plus 9. That's the sigma that is going through my brain when he says sigma is this thing, right? That's for adding up macroscopic changes. What symbol did you use in calculus to add up infinitesimal changes? I don't even know what it's called. What is that called? You know what I'm drawing? I have to draw it this way, right? Because you're facing me. The integral sign. But there's no name for it, is there?
Just integral.
Yeah, but it's... Right? What's the name of that? I don't know. Integral sign, I guess. Okay. We want to get a number. We got a number for W is minus P external delta V. You get a number for the joules. You get a number for the area. That means we have to have limits. So dW, I don't know. W1 to W2 or work initial to work final. I don't know. It doesn't really make much sense, but right? Okay. Now what are you going to do for limits on here? Why is it V1 and V2 or V initial and V final? Because you look at the dV. That's what's changing, right? And you know pressure's constant, so okay. V1, V2. Okay, we're getting there. So you integrate this guy, you just get. They don't like you to write delta W or anything. You just write W, because when you write delta W, it really means work final minus work initial. It really doesn't make much sense because there's work. If you follow a different path, do you get a different distance? Yeah, if you're talking about just walking on a trail. If you take a different path, would you get an overall different distance? Yeah, right? You would, right? So that means distance is not a what function? State function. Work is not a state function. I could waste a lot of time raising that syringe. I mean, I could go up this way, go back down. A gazillion different paths to go from the initial to the final state. Work is not a state function. That's why it's poor practice to write delta W. You just write W because it's not a state function. Okay, so that's why I just write W, not changing W or anything. Now, can I pull, we want to do this integral, can I pull the P out of the integral? You have to always ask yourself this before you pull something out of an integral. Does P depend on volume, right? Because if it doesn't, you can pull it out. It's like a 6. You can pull it out. Does P depend on volume? If I give you a volume, can you calculate a pressure? Yeah, you'd use what equation even? PV equals nRT. So that means pressure definitely depends on volume, right? Because if I give you a volume, you can actually go calculate the pressure. So if it depends on it, you better substitute in how it depends on it, right? So you said PV equals nRT, so P is really what over what? nRT over V. You better substitute that in for it. Okay. Now again, what can we pull out of that integral to make the We can pull out what? Definitely the R, right? Gas constant. Can you pull out the N? N depends on V, right? It's right in there. So now you got to start making the assumptions. If you pull N out, you have to say, what about this gas that you're studying? This 1 mole, 2 moles, 3 moles. It just can't change. You can't be adding or removing substance. N has to stay the same in this process. Whatever the process is, you can't change the number of moles of gas. You can't change the number of moles of gas. So, okay, we'll pull the N out then. We pulled out the R. Okay, can you pull out the T? Can you pull out the T? Here's a hint. We want to end up here. What are we going to calculate? How is it described? Isothermal reversible work. Well, that means T is constant. It has to be. Otherwise, this equation is not valid. T has to be constant. So pull it out. V1, V2, 1 over V dV. Okay. What is the integral? What's the antiderivative of 1 over V? It's natural log, right? Let's see. So you remember our notation. Notation is really going to help you. Right? Did I forget something?
You forgot your negative. You can take out that negative, but you have to keep the pressure inside.
Oh, hold it. I forgot 1 over natural log of V.
Not on negative pressure on P.
Oh, I dropped my negative way up there. Shoot. Yeah, do you see what Juan's saying? There's my negative right here.
I think that's the only.
I better have it there. Better have it there. Better have it there. Right? Forgot my negative. I was wondering how we're going to get a negative. All right. Thank you very much, sir. Now, again, notation really, really helps you because if you write the notation, it tells you what to do next. Right? So I'm going to put in V2. Well, they didn't, in their equation, they didn't have V2, they had VF. But I'm going to put in my V2. It's minus what I had for the V1. So minus nRT. All right? Natural log of V2 minus natural log of V1. So what can you do? What do you do when you subtract logs, natural logs or regular logs? LOG? You divide. Yeah. Minus means divide. So this is the same as natural log of V2 over V1. We got it. That works. Okay. If you do things infinitesimally slowly, you have to integrate. Okay. So let's jump back a little bit. Make sure we're all following this here. In this one, this picture right here, with energy going out like that, for all processes, delta U is Q plus W. Right? We're keeping track of energy. With that diagram, what would be negative? Anything? Or what would be positive? Kathleen. With that energy going out, would that be negative or positive energy? Negative, right? And they're not really specific here. It's more than likely Q or W that's negative. What would you guess? I'd say Q2, right? But it's not really clear. It could be a piston moving out. You're not transferring matter, right? So it's really not that clear. But the point is playing around with the... How about if you had isolated? Can anything ever be negative? can't. Right? That's the idea of this whole universe having a constant amount of energy. Can't change. What else did we talk about? Oh, here's a good one. I don't think we hit on this one very well. What was Na? Avogadro's number. To me, it's better to write this. It makes more sense if the book would have done this. K is R over Na. Because K gets things down to the molecular level, the atomic level. What's that gas molecule flying around? Because you're dividing the gas constant by Avogadro. Right? And so really what that makes, we're so used to using R. And K is really where it's at, because K is at the molecular level, how much energy is going with that one single molecule. That's what the Boltzmann constant is really getting at. Energy in individual molecules. Gas constant is really just a molar Boltzmann constant. It's the amount of energy corresponding to a mole of gas molecules. Okay. And then they got into the Boltzmann distribution and how different numbers of molecules are traveling at different speeds. But it really came down to this. This is the part that is really applicable, is that these little gas molecules can move in how many possible directions? 3. So, well, if they can move in 3 possible directions, that means in each direction it's random. So it should be an equal amount of energy in every direction, X, Y, and Z. So that's what it turns out to be. And notice that the K is in there, because K has everything to do with the energy per molecule. Okay, so you have the exact same 1/2 kT, just added up 3 times because there's X, Y, and Z. Divided the total energy 3 different directions. And then they put in the R, because R, like I said, is that molar gas constant. Right? It's the amount of energy regarding the amount of moles. So that means little n is what? Is that the same as the little n in the PV equals nRT? Yeah, because it's number of moles. That's what little n is, number of moles. Remember, we're kind of a new way of looking at the gas constant R is it's the energy regarding a mole of these gas molecules. Okay, where K, here they're talking about a single gas molecule, aren't they? Little m, a single gas molecule. Single gas molecule, energy in X direction, Y direction, Z direction. Okay. And then we had stuff like this. Why is that always 0? And it has to be for a perfect gas, exactly. And why? Temperature's constant. The only way to change the energy of a perfect gas is to change its what? Temperature. That is the only way to change the energy of a perfect gas. You gotta change its temperature because they're dots. Okay, I think Alice can show us how to do some problems now, right? Okay. 2.1, 2.2, and 2.3. Oh, I'm on the 2.1.
Scares me that there's only 3.
I know, right?
They're taking it easy on you, I think. 'Cause I skimmed through the questions, but calculate the work done in A. Oh, don't we have them typed out?
Yeah, we do.
You do. I don't. Where are they?
No.
It's further down? How did you... I must have the wrong thing typed up here. Okay, well, you have them typed. I'll have to add them later. 2.1. Thank you, sir. Calculate the work done to raise a mass through 10 meters on the surface of the Earth, the Moon. Oh, well, what's the equation for that? Work is what times what? Force times distance. And the force you have to use is the object's
Weight.
weight, right? Mass is in the force. So weight, so that means it's going to be weight times distance. And the equation for weight is? Yeah, mg. So that's not so bad, right? Man, they even gave you everything in the right units. Jeez. Okay. Calculate the work needed. Okay. Does anything change for 2.2? Pretty much the same question, right? All right. 2.3. Chemical reaction. Okay. 2.3. You have a reaction, and they give you the area of the piston, right? And this piston's pushed out through 10 centimeters against an external pressure of 1 atmosphere. They want the work done. Seems to me we have two possibilities there, don't we? Don't we have these two possibilities? Right? Which one is it? Because you can get a different answer with those two questions, those two equations. Which one did you use, Alice? You didn't do that one? Use the first. You used the first one. Juan did use the first one. Now he's right. Why? Did it say irreversible? Yeah. Well, you can have. You'll have an external pressure on the reversible one too. Yeah. But you could have a.
Isn't it reversible because the external pressure is equal to the internal pressure?
For I think for something to be done irreversibly, you need some special situations. You got to be doing things really, really carefully. And it's going to be saying it. It's going to be saying infinitesimally slowly. It's going to say reversibly. Because it doesn't. They're just saying go out in the lab and do it. That's the language that they're saying. You just go out in the lab and doing it. Well, that's a macroscopic change. There's only one situation that I can think of that maybe you put it on this quiz where you have to realize what's going on is actually a reversible process. What am I talking about? It actually happens there in the lab. And it's really the only one that I can think of. We can do it right now. We don't have, no one's, you guys bring drinks, we don't have any ice. Have ice sitting there. And energy's going, right? You have solid, liquid, gas. Which one is the lowest energy form? Solid, liquid, or gas? Which one is the lowest energy state? Solid. And then the highest energy would be the gas. Because all you're doing is adding what to go from one state to the other there? Adding energy. What type of energy? Heat. Right? Okay, so one is more energetic than the other one. Melting is a completely what process? Irreversible or reversible? It's reversible. Because imagine you got that little ice cube sitting there melting, right? Well, you can put it back in the freezer. Get back to where you were. So technically, you just wouldn't want the little droplet to be running around and stuff, because then you have interactions. You have to kind of keep track of all the what's going on at the molecular level, and you have the little drop, surface tension breaking. You have stuff going on there. No, you can't have little droplets rolling around. Right? It's just the state microscopically of it melting, and then putting it back in the freezer. It freezes back. So you're not letting stuff move around on you or condense. Okay, but so that's the only situation that I can think of where they're not going to say this is done reversibly, but it actually is reversible. So that's all I really have. Hate to let you go early. Okay, so check out, get the homework done, and do the bold words for the next section. I'll try to get those exams back on Friday.
Who was it? Somebody had a case on their phone, and they were like, yeah, man, I love it. Watch this. You just check the word problem. Just check the bounce off the ceiling, roll them, on an iPhone.
Oh, there's stuff in your folders if you haven't got it.
This
You just need a bell on your keys.
4 centimeters to meters.
Yep. Yep. This should be centimeters squared.
Oh yeah.
Would you
Yep.
just change it to meters?
So
Mm-hmm.
then it's just over 100, and then the all squared.
Yeah, so divide 100 by 100 squared.
Okay.
Yep.
Hopefully I got it right.
That's good.
Because it's...
Because then you can do. Because what I did, I got the for volume, just area times distance, or so.
Yeah, cross-sectional area
the
times the
cross
height.
times the height.
Yep.
Okay, so then I use this. What they're moving it, it's pushed out. 3
Yeah,
centimeters,
that's
so
how you,
it's
that's
not
how you're gonna
height.
get your volume.
Yep.
Exactly.
Yeah.
Yep. You got it.
Taking physics and this at the same time.
Thank you.
Can't math.
I could have some good questions on the quiz next time.
Still checking the vocabulary. I didn't know we were supposed to turn it in last time.
You can turn it in. Just turn it in with this one.
What is this? I already know what this
Just
is.
turn it in with that one. You just have to find it and staple it. I think I forgot to ask to have you turn it in. I don't really quite recall. So what's permanganate?
Nope. I'm not the one being tested on this material, Dr. Smith.
You know what it is.